welcome all. Uh, Today is the public talk by Prof Saket Saurabh. This talk actually is part of our series on Azadi Ka Amrit Mahotsav, where we are celebrating contributions of India in the last 75 years. So, of course, our institute is organizing these talks to also celebrate Indian science, and today we are celebrating a proud moment for our institute, which is the recently awarded Bhatnagar Award to my colleague Professor Saket Saurabh this year in mathematical sciences. I am not qualified to talk about my colleague Saket, who is the inspiration to all of us. So to talk about Saket the Arjun, so I invite the Dronacharya, Professor Venkatesh Raman, please. And Professor Venkatesh Raman will today moderate the event. Thank you very much.
Thank you. I must say that this Arjun need not require an advice. If any, he became my Dronacharya pretty soon, except that I have become, I'm far from being an Arjun. So it's a pleasure to introduce Saket, who I had the privilege of knowing for the last 20 years. I knew him from his BSc days. He did his BSc and MSc at Chennai Mathematical Institute and PhD at IMSC Chennai. And during PhD, he visited University of Bergen a couple of times. The second time was during his long gap between his thesis submission and defense. And soon after his defense, he became a postdoc there. And in 2009, he joined IMSC as a faculty. He also holds an adjunct faculty position at University of Bergen. So he has several firsts to his credit. Let me start with something I'm not 100% sure. He's probably the first alumni of IMSC to win the Bhatnagar Award. Okay. Nobody is disagreeing, so I hope it's correct. He's the only person to have a non-European PhD and has won the prestigious European Research Council grant. Not once, but twice. He has an initiation grant and he also had a foundation grant, and I think it still stands that he was the only one non-European PhD. He was the first recipient of ACM India's Early Career Research Award. This was instituted last year. He's a fellow of the Indian Academy of Sciences, European Academia. He has won Microsoft Research Outstanding Young Faculty Award and Swarna Jayanti Fellowships. So he has co-authored a couple of textbooks and several influential surveys in this area of parameterized algorithms. He has mentored more than a dozen PhD students and an equal number of postdocs and masters and undergraduate interns. He is also in the editorial board of several computer science journals. The reports about him you would have seen after he won Bhatnagar, they don't talk about the number of papers he has written. It's not because he has not written many, but he has written an incredible number of them. You can go and check DVLP Saket Saurabh and just make sure that your system has enough memory, it doesn't crash your system. For example, in the year 2021, I just checked, he has 13 journal papers, 16 conference papers. In computer science, conference papers are a big deal. These are conferences with 20 to 25% acceptance rate. And a few more in archive, and I realized that there are 18 more days left in the year. So this number will only increase. So now how does he do it, right? It's almost a cliche to say that, the speaker doesn't need introduction, but I am going to depart from this and give a very long introduction and, give a recipe for his success, having seen him in close quarters in the last 15 years, because after all, these events are not just to celebrate, but also to inspire the next generation of researchers, right? So, in my opinion, he is a standing example of the quote that success is 1% inspiration and 99% perspiration. Okay? So I'm going to give you 5 recipes for his success at the risk of embarrassing him and probably boring you, but hopefully this new generation of researchers will pick up some tips from here. Saket has a great art of finding interesting questions. Every talk or a paper he reads is an opportunity not just to learn some cool techniques, but also to identify interesting questions not for him or for his students, questions that can engage the entire research community for several years. In fact, the deep connections he makes with these questions to some of the questions that people have been working on, it helps a conference reviewer to appreciate your work. So in particular in a computer science where there is a conference culture and you have a reviewer who may not be a subject expert and he has a very little time to appreciate your work, putting your research in the context of a number of other related questions is an art he has really mastered, I would say. I would suggest you to go and read introduction of some of his papers. They usually tell a story. Number 2, every time he has an idea or he learned something, like a crow, he has to call everybody and share. Okay. Now, if it's on a research project, he will share with his collaborators. If it is some paper he has digested, he will give a talk. If it is a set of papers and a theme he has understood now, he will give a course, whether it's a summer course, winter course, NPTEL course, or he will organize a conference. And this is how he has expanded his collaborators and written popular surveys and books. Now, it's not enough to find the problem, find collaborators, and write a beautiful introduction. You need to solve the problem, right? And how does he do that? I'm going to paraphrase one of his active collaborators who says the following about him, his art of, reading papers. And he says, Saket knows everything, to the extent that everything in a field can be known. There is not a new paper within our primary subfield of parameterized algorithms and complexity that he has not read and digested within a few weeks of it showing up on archive or being published. This is of course an exaggeration, but not by much. But the following is not an exaggeration. When I am wondering about the literature on some topic I am not too familiar with, I will first ask Google. If Google is not helpful, I ask Saket. Quite often, Saket knows what Google does not and is able to point to a lemma in the middle of an obscure paper that is phrased in a totally different terminology than how I asked the question, with the remark, maybe this is helpful. And fair enough, after 30 minutes of digestion, that lemma turns out to be exactly what I was looking for. How he does this, I have no idea. And he has this ability to, tread to new areas, go beyond his comfort zone. And this is again, his friend, active collaborator says, he wants to know everything also to put to use right now, often before even fully understanding what is it good for. I remember him telling me that we absolutely had to learn exterior products, a fairly advanced topics in algebra. So we spent a few days trying to dig through it until I essentially gave up. This is his collaborator. But Saket persisted and a few days later explained how exterior products could, for our purposes, just be translated into properties of matrix determinants, and that's probably was just what we needed in order to solve a seemingly unrelated problem that we had begun working in a few weeks earlier. A few days later, we had the main results of what became an important paper. And finally, about his work ethics, which we have all seen, Saket leads by examples. With a small child, a substantial teaching load and departmental responsibilities, he's able to stay on top of everything, coordinate everything, write a substantial fraction of the gazillion manuscripts under submission, and ensure that everything is in shape by the deadline. Again, remember, our conferences have deadlines, right? It's not something you finish and send whenever you want. How he does this, I honestly do not know. I believe he occasionally sleeps. Okay. Now, so these are in my opinion, the 5 recipes, right? Ask interesting questions, share the knowledge, read a lot of papers, go beyond your comfort zone, and work hard. Now, for the people who are in this business of mentoring students, this is what his friend has to say. I completely agree with him. It's just that he has articulated it much better than what I would have. And he says another amazing quality of Saket is that somehow he is able to make everyone around him do better, especially in his students and postdocs. Basically, all of them go on to do much better, both in terms of the science they produce and in terms of their careers, than I would guess from sizing them up. Somehow, he invariably manages to make everyone around him better learners, better problem solvers, better scientists overall, while making people also feel better about themselves. I think it's a mix of natural talent, a really conscious approach to help people achieve beyond what they themselves think is realistic, being able to identify people's unique talents and matching them with research directions in a fruitful way. I do not think I know of any other person who even comes close to matching Saket as a research supervisor and mentor. Okay, so with these few words, well, more than a few words, I wish him many more laurels, and I invite him for the talk. Before that, our director has some more things to say.
I think, Venkatesh has said everything that we would like to hear. In fact, Saket is an inspiration for not only for youngsters, he is an inspiration for many of us actually. I moved to this institute in 2012, at the end of 2012, and I knew his existence even before I moved in here. And I was lucky that I was also, given a room very close to his office. And I have seen his name when I joined, but he was not here at that time because he was abroad somewhere. And I wanted to meet him and I wanted to see him because he was considered star and he's still considered star. Okay, and I still remember. And his presence was felt the day he reached, not because he showed up, outside his office, because there were crowd outside his office. There were several students standing outside, and I could hear loud voice inside, and it was definitely, Saurav's voice, because nobody will miss his voice, even if the doors are closed, actually, because he's always loud. And it's not disturbing, of course, and you could see a lot of people outside waiting for him to meet. So then I realized why he was called star, and he's indeed a star. And in fact, I'm proud of two reasons. One, he's an alumni of our institute, so we all are proud of him, one. And two, is my colleague actually, and I'm really honored to be his colleague. And institute actually, take lessons from him, particularly the way he actually spends time in doing, the science that he is doing. That is very visible actually as a person who actually living in the same corridor. I see him actually. I've never, had a day that Saket is absent, because he's the most noisiest person in our corridor, and I am proud to say that I was the noisiest person, because he has really attracted, great minds and taught lots and lots of students. You see, variety of students standing. It's not the same set of students, for last 1 year. It's the faces are new. So that really shows that how active he is, how attractive he is, as far as the kind of science that he is doing. So it is indeed great honor to have him here in our institute as our faculty, and I think he'll do more achievements in his life and make all of us proud, and also inspire all of you. more, and I will see more Saket in future in our institute. Thank you.
Now invite our registrar, admin officer, accounts officer, and Professor Ravindran to felicitate Saket.
Thanks, Ravi. Thanks, Venkatesh, for such a wonderful, or let's say, I have no words to comment on that for the introduction. Yeah. So, but before I give my talk, let me use this opportunity to thank people, because I have grown up in this Chennai from long time. I came to Chennai in '99 to do my undergrads, and I did my master's, my PhD, and then for a couple of years I was at Bergen to do my postdoc, and from that time onwards I'm back in Chennai. So this journey has not been like, I didn't know what computer science was, and I remember when my first exam happened, and like for Pascal, and I remember that they asked us to multiply, design a program in Pascal to multiply two polynomials, and I think for 3 hours I was like wondering, like, because all I have seen in my books is that you write x squared plus 2x, how will we take an input from user which will look like x squared plus 2x on the screen, and 3 hours was passed. So from that, and I remember that I going to Kumar's office and talking to him for hours, and then I got to realize what it means, how computers actually work, how computers think. So in those days, we could walk, I think the same is true even now, we could walk into anyone's office and somehow people had time to discuss with you for ages. So like I had similar issue with Turing machine, and Kumar spent, I think, I don't know how many times he explained the Turing machine again and again and again. Finally, in a few weeks, it got, I understood it. So it is an investment from lots of people, especially when we were growing at CMI. So people like Kumar, Madhvan, KV, and Deepak, who moved to ISC, spent lots of time explaining to us every tiny bits of this. And then Venkatesh taught us an algorithm course in 2001, and which I really liked. And I followed it up with doing my internship with him, and he gave us a problem in parameterized algorithms. And I think from that time I have been just doing that. So it's like, I don't know, some 20 years that I have been doing parameterized algorithms, starting from the question which he gave me. And I didn't know why it is important or why it was good, but combinatorially it looked challenging and interesting. And then when I was in my master's, I did lots of courses at IMSC, and like with all the faculties here which were there at that point of time, like Meena, Venkatesh, Arvind, CRS, Jam, and Kamal. So I mean, all this teaching has shaped us how we are today. And I would also like to remember one thing which happened, and during the time, so as Venkatesh was pointing out, right, like this idea to learn new things. So I don't know if Meena remembers that there was a talk by Vigderson at FST like invited talk, and we decided that we need to understand this talk. So we learned a couple of papers by him as like internal seminars, and then we went for his FST talk. So this idea of learning new things like was all there in the, let's say, atmosphere at IMSC and CMI, and it's just that you just inculcate some of these things and you do. So I have tried to just maintain those small values across, and it just has worked out well. So thanks to all these people. And then I moved to Bergen. I was really very fortunate to find 2-3 people equally passionate about what they were trying to do. It was Feder and Daniel, and Mike Fellows was visiting at that point of time in Bergen, and he would sit across all the tea times and coffee times and give you all these big ideas, which looked just very very vague, but when we tried to work it out, we found lots of gems there. So he was very generous with his ideas. So that also told us that, if you're generous with your ideas, it's not that, you will lose, but you rather win, you gain. So these ideas of mentoring students and all these things came from being in the close quarter of this set of people. So thanks to all of them. And then I've been really fortunate to, followed up with, I had lots of great students and PDFs and lots of collaborators, and they have actively contributed to my own thinking, and they've also been nice in the sense that even if I pinged them in the middle of the night, they didn't object to it. So, or with MSR, he used to wake up at 3 o'clock, I don't know why, and we used to have most of our science discussion around 3:30 in the early morning. So it was great. I found someone always, if I wanted to talk to at some part of the world, if I wanted to talk to at any point of time. So that was a great learning experience in last 10-15 years. So thanks to all of those people. And finally, nothing is possible if there's no family support at home. So I had great family support at home from my wife, my parents, my siblings, and now with my son around from last 4 years. It has been great, wonderful experience when I go back home playing with him. Just calms you down and you can start fresh, think. So thanks to all of these people for making this journey wonderful and happy. So with these words, thanks to all of you. And with this, I will try to give you a small talk on coping with intractability using parameters. So let me tell you one thing. So I am not very comfortable in giving public talk. I have shied away from this for a long time, but maybe this is my opportunity now to give my talk to slightly mixed audience. I have given several talks to all kind of audience, but maybe this is my first talk to a very mixed audience, and I will try my best to keep it a level which is accessible to most people. So with that, let me start with my talk. Okay, so this is a very natural dilemma which people have whenever you have to give a talk, like what should I talk about, how should I talk about, and what part should I tell or what part I shouldn't. So I also went through this dilemma, and based on that, I decided to talk about at least large part of my talk about story about some what I call tech-savvy security guard. And then I will tell you a little bit about what do we mean by intractability in theoretical computer science, and couple of thoughts. Okay, so here's a story of tech-savvy security guard. So here's a Gram Panchayat, and imagine that you're exceptionally tech-savvy security guard of this Gram Panchayat in a small village in India. Okay, and every Friday night, Gram Panchayat meeting, and half the inhabitants of the village come for this meeting. But unfortunately, these meetings are well known for lots of fierce arguments and resulting in these nightly fights. And so this results in excessive amount of work for you. Like having to throw out guests is tedious and rather unpleasant task. So you decide to take some preemptive measures that you don't want to, be throwing people out during the meeting, but rather preemptively decide not to allow some people to the meeting. And so village is small, so you know almost everyone, and you also know how likely are a couple of people to fight with each other if they are admitted to this meeting. So you have this set of information because the village is small. So you wish to plan ahead, and you only want to admit people if they will not be fighting with anyone else at the meeting. So this is your goal. So you like to admit people to this meeting if you know that they will not be fighting with anybody else. At the same time, the committee members want good participation. So they give you some number K, and they say, look, we are not too happy if you disallow most people, but I give you some budget and say, you're only allowed to disallow some K number of people. So K could be 10. So you have to allow all but 10 people to this meeting if they wish to come. Okay. So now what are you left with? You are left with the following optimization problem. Okay. So what do you have? you have a list of all these n people who like to come for the meeting, and for each pair of people, a prediction of whether they will fight if they both are admitted. So you know a list of people which is like, oh, if these two people are admitted together, then they are bound to fight. Okay, and what you need to figure out is the following: whether it is possible to admit everyone except for at most k troublemakers, such that no fight breaks out among the admitted guests. So that's our question. So you have this n people, and you have these pairs where you know that if you admit these two people together, then they will fight, and you like to admit all but k people without having any fight in the meeting. Okay, so let's, for brevity, let's call this GP5 prevention problem. Okay, from Friday you should remember from where this question comes. And here's an example. Okay, so here's an instance of GP5 prevention problem. So here are people named. I on purpose wrote non-Indian names so that I don't hurt anybody else. Okay, so here are some names, and if you notice, the line between two people tells you that if you're going to admit these two people together, then there will always be a fight, or there will always be a conflict. For example, if you're going to admit Bob and Daniel together, they will fight. But look, there is no line between Alice and Daniel, which means that if both of them are there, they will never fight with each other. But if you admit two people which has a line between them, then you are bound to have a fight. And if you notice, if you decide not to admit Bob, Daniel and Federer, if you decide not to admit these three people, then rest of the people has no lines between them, which means that these people will not fight in the meeting. Okay, so here's a simple example. So basically, so this is an example of a small instance or example of this other problem of GP5 prevention problem. And if you notice that if I ask you the following question, can you just stop two people and have set of peoples that there is no lines between them, you can see for yourself that it is not going to happen. So if you look at this one, Federer and Eric, there's a line between these two. And there's also a line between Christos and Daniel. There's a line between Alice and Bob. So if you notice this line, and this two lines, they're like independent set of people. Like whatever you do, you know that you need to at least admit or not admit one of these two people. You have to at least not admit one of these two people, and you have not to admit one of them. So this just tells you some sort of lower bound on how many people you might not admit. Okay, so this instance has a solution with k equal to 2. Okay, unfortunately, this GP5 prevention problem is a classical NP-complete problem, and those who might have heard under the name of vertex cover. Okay, but so what does NP-completeness means? I told you, like, just means something very difficult, and this is what I mean by intractable, and I will explain to you what I mean by intractable in next few minutes. Okay, so here's the following known open problem about GP5 prevention problem. So the question is, does there exist an algorithm with the following things? Can you have an algorithm with 100 n operations? Can you have an algorithm with 100 n square operations? Can you have algorithm with 10,000 n to the power 100 operations? And if you found, oh, too much time is given to you, maybe just take as much as your time believe, like here's some big n to the power some polynomial. Okay, and still an open problem whether we have such an algorithm or not. Okay, so if you notice, this is like some x is like some 2 to the power, I don't know, as much 2 I could put in my slides, I try to put, and n to the power this. But look, when I say x to the power x, it is this to the power there. Okay, so it's really, really huge number. Okay, so we do not even know an algorithm or with that many operations. Okay, so there are two possible explanations for this. Okay, so what are the two possible explanations that we do not have such an algorithm? Well, no fast algorithm for this problem has been found so far, because either no one has been smart enough, that could be one reason, or it doesn't exist. And we like to believe it doesn't exist, but we still do not know how to prove it. But what do we know really, what to show about this is following. So suppose you're working in a company and your boss asks that, hey, you need to make a vacuum cleaner, but vacuum cleaner with some specification, like it should rotate, it should dance. I mean, you could add any specification you wish on this vacuum cleaner. Okay, so your job is to make this vacuum cleaner with some specification. You think for a little bit and say, or you give up after a few days, and you ask your more intelligent friend Sheldon and say, hey, can you help me make such a vacuum cleaner? He also thinks for a few days and he says, nah, I don't know how to do this. But I also know a much brighter friend than myself, and let us go to him and let's see if he can make such a vacuum cleaner. So he goes and finds Einstein. Einstein says, okay, he's a smart guy and one of the most smartest person of our era. He also thinks about this for a long time, that can I make such a vacuum cleaner? After a few days of thinking, he comes back to them and says, look, I mean, I don't know how to make this vacuum cleaner, but I know something more fundamental. That if we could make such a vacuum cleaner, I could do the following amazing things. Like what? I could make a time machine. Okay. I could make a unicorn bunny, or I could do a cold fusion, or probably I could make a ship which is faster than the light. Right? So if we could make this amazing vacuum cleaner, then I could make this amazing set of things like time machine, unicorn bunny, I could do cold fusion, or I could travel faster than time. And so interpretation, and up to you to interpret this answer. Like if you're a pessimist, you would say this means that such a vacuum probably doesn't exist. Or you're probably optimist and you would say that let's pour all of our resources and let's make one such vacuum cleaner. So it's up to you how you want to interpret this answer. Or maybe you're a realist and you say, let's find some way to get rid of this. Like let's find some coping mechanism knowing that these things are hard. So it's up to us what kind of people we are, what kind of person you are. Okay? Now, so what about GP5 prevention? So like what is the analog of Einstein and the problems which we said for this GP5 prevention problem? Well, we had this amazing set of people, I think it's Cook, Karp and Levin, okay? So they are like your Einstein, and what they showed, that if you could have a fast algorithm for this problem, this GP5 prevention problem, then I could make this time machine, unicorn bunny, cold fusion, and this, ship which travels faster than light. Not actually, but something very close to it. Let me show what. Okay, so this is where it comes about something called verifying solution. So what is a verifying solution? So if I told you, here is my instance, I said, I'm not telling you to find the solution. I say, hey, is it true that Bob, Daniel and Feder, if you don't allow them to come to this meeting, then all the other people will not fight? You notice, if you don't delete, then look at Alice, Christoph, Eric and Gerhard. There is no line between them. Between any pair of them, there is no line. There is no fight. And if I told you this solution, you can definitely check it. You can definitely verify it. So we can efficiently check whether a proposed solution is correct or not. Okay. So it seems easier to verify whether a solution is correct than it is to find one. Okay. I will give you a very good example of this. So when I started up as a faculty, okay, I used to worry when I used to give this assignment problem. I used to solve them and say, look, if I have to, I should be able to solve them before I give it to them. Okay. But after a long time, I realized that what did I learn in my complex? I don't need to worry about whether I can solve them. All I need to be able to do is once the student does it, I should be able to verify it whether it is correct or not. So solving is always harder than checking, verifying, or correct. So this is exactly the same analogy here. Right? I may not be able to solve the problem, but I will be able to verify the solution. Okay? Okay. So what these people showed us, these bright people, is that if you could have fast algorithm for this fight problem, then all computational problem that one can check solution for quickly can also be solved quickly. So what did he say? That look, if you can make this amazing algorithm for this problem, then for any problem where you could verify solution, I could also make one such solution. Okay? And here's a problem of factoring, where if I give you such big number, you may not be still have hard time designing good algorithm for factoring, but if I give you two factors, you can easily verify it whether it multiplies to this number or not. Sudoku, right? If I gave you this Sudoku example, like filling it up is difficult, but if someone filled it, it is easy, right? All you have to say, the sum of these 16 numbers is same, the diagonals are same, and all these simple properties that you need to check, right? So verifying is much easier than finding the solution. Okay, and this kind of situation arise in multiple situations like airlines planning and like SIP and chips and you name it. Okay, so GP5 prevention is not an exception. So what these people showed, that there's a fast, if I can design a fast algorithm for this long list of problems, then that implies that all computational problem that one can check solution for quickly can also be solved quickly. Okay, so this is my analog of if you could make your vacuum cleaner with such specification, then you could do some amazing set of things in physics. Okay, and this is the basically this classical well-known open problem of P versus NP, for which you have $1 million prize money, and from the Clay Institute, which still remains one of the most challenging open problem in the area of computational complexity. Okay. Okay, so, and unfortunately most optimization problems are NP hard. Okay, and so what does it basically mean for normal, like if you do not want to get into the technicality of what it means technically, then what it actually means is the following simple words. No algorithm solves all instances optimally in polynomial time. So for all engineering purposes, for all practical purposes, we could take this definition and work with it. That what it means, that there is no algorithm solving all instances optimally in polynomial time. Okay, the reason I wrote this, because if this is how we take it, there are lots of ways of designing coping mechanism which tries to relax one of the things which I have wrote in this slide. Let me go over one by one. Okay. Okay, so solves. So we have this algorithmic paradigm which is called kernelization or polynomial time preprocessing. I will come to that in a minute. And all instances, so you forget about trying to design an algorithm for a problem on all instances, but you restrict your input. Okay, and there are also the notion of parameterized algorithms comes, which tries to be nice or tries to be efficient for certain values or certain kinds of inputs. Optimally, so this is the most classically known paradigm to deal with NP hardness, or is that you forget about solving the problem optimally. You say, if I give you so much of time, can I get close to the solution? Maybe I cannot find a solution with 3 people, but maybe I'm happy with 6 people. Maybe I'm happy with 10 people, right? So this is an area of approximation which has developed over the last 3-4 years with extremely deep mathematics. Okay, or we could relax this idea of polynomial time, say, okay, I still want to get a very good solution, and I allow you time which is beyond polynomial, like you could take some exponential amount of time. So this will be slower algorithm, but could we do better than what naive algorithms could do? Okay, so these are the kind of areas which leads, if we try to say that, okay, this is hardness, how could we deal with hardness? So either you try to restrict your input and solve it, or you try to solve your problem not optimally but approximately. You try to take more time
than what polynomial time allows you to do so. So these are the kind of things that you relax and you try to deal with. Okay. So let's go back to our fight prevention problem. Let me give you a couple of algorithms at least, which is, okay. So if you recall correctly, you had n people who would like to come to this meeting, and you have this prediction between pair of people who could fight, and your objective is to possibly admit everyone except for k troublemakers such that no fight occurs between the admitted people. Okay. So one way could be, let's solve the problem by trying all possibilities. So if you recall, we had 1,000 people. So one way could be that let's try all possible subsets of people that we would like to disallow. And I told you, you could check the solution easily. So you try to check, is this subset of people, if we disallow, will there be no fight? I try all possible people. So how many subsets are there? Roughly 2 to the power 1000, which is like 1.07 into 10 to the power 301 possibilities. Just 2 to the power 1000. Okay. Program won't terminate before the guests arrive. In fact, probably not even before the universe implodes to itself. So just 2 power 1000 is such a big number. Okay. Luckily, I told you, right, the number k of guests that should be rejected is say small. K is at most 10. Okay. Then we do make a progress, because now I don't need to check all subsets, but I only try to say, are there some at most 10, or there some 10 people that we could exclude from coming to the meeting and there will not be fight, because then all I need to do is to check 1000 choose 10, which is like 2.63 into 10 to the power 23 possibilities. Much better, but still quite impossible to do in one day, even with access to supercomputers. So even though it becomes easier, still it will take a lot of time even on supercomputers. Okay. So do we give up, resign to throwing guests when they arrive at the meeting, or we could do something? Okay. So here are some simple heuristics or simple pre-processing rules that we could try. One thing is, try to easily identify some peaceful souls to accept and some troublemakers to reject, right? So let me mean what I mean by peaceful souls. Well, peaceful soul, anyone who does not have potential conflict with anyone else can be safely included to the list of accepted people. If I know this person doesn't fight with anybody, like we could just put, yeah, you come, because you will never create fight with anyone because you don't fight with anybody, right? So these are like peaceful souls for me. I could always include them into my solution. Who are troublemakers? I mean, there are people who fight with a lot more people than some people. So I have quantified what I mean by troublemaker is that if some guy will fight with at least say k plus 1 people, other guests, you have to reject him. Why? Because if you don't reject him, then who all you have to reject him? You have to reject all other k plus 1 people he fights with. Because if he comes and anyone else of these k plus 1 people will come, there will be a fight. So you have to reject all these k plus 1 people, but your management or the committee has asked you only to reject k people. So rather than rejecting this k plus 1 people for which you do not have budget, what you decide is to reject him. Okay? So here's my definition of peaceful soul, here's my definition of troublemakers. Okay, and here's an instance of my problem, and if you notice, Daniel is such a troublemaker for k equal to 3 because look, he fights with 1, 2, 3, 4 people. So if I'm looking for a solution with just 3 people, like if I only want to throw 3 people, then I must throw Daniel, because if I don't throw Daniel, I have to throw Bob, I have to throw Christos, I have to throw Eric, I also have to throw Gerhard. That is 4 people, right? So what's my rule? My rule is very simple. Once we identify a troublemaker, we remove him from the guest list and we reduce the number of people that we need to throw drops by k minus 1. So here I will throw Daniel out from my list and say, look, in the remaining set of people, you're only allowed to remove at most 2 people from the list. Okay, so this is what is my rule for troublemakers. So and that's it. So my rule for peaceful people, always accept them to the meeting. If there's a troublemaker, then move him from the list of accepted people and drop the number of people you could reject by 1. Okay. If there is no one left to strike out in this manner, then we know that each guest will fight with at most k other guests, right? We have ensured that, okay, I'm not able to find any troublemaker. What is the meaning of that I'm not able to find any troublemaker? Means every soul fights with at most k people. So rejecting any single soul, if you reject one person, how many conflicts can you resolve? At most k conflicts. And if you have k people, how many conflicts in total can you resolve? K square. One person can, if you throw one person, you can resolve k conflicts. So if you throw k people, you can resolve k square conflicts. So if there are more than k square potential conflicts, then you know that there is no way you can throw just k people and be happy. There will be a fight, so just brace for it. Okay, so otherwise what happens? You know that each guest who has not yet been decided has the following thing. He participates in some fight, because if he was not participating in any fight, we would have. And every person participates in at most k fights or k conflicts. So how many people's fate has not been decided? Notice that each conflict there are 2 people at the end. So if there are at most k square conflicts, how many people's fate has not been decided? About whether to admit him or not admit him is like 2 into k square. Okay, so now let's try, after we have done so much of pre-processing, we don't know what to do more. We could try now 2k square choose k, which is like 200 choose 10, which is feasible to do in less than a day on a modern supercomputer, but quite hopeless on a laptop. So hoping that a security guard in a village has a supercomputer is hopeless. So it's still a useful solution, but still not too useful for the security guard. Okay, but this idea of trying to find some way to reduce your instance, reduce your input, make something smaller, is what is called, and with some provable guarantees, what is known as mathematical preprocessing or kernelization. Okay, so this is this way or this art of reducing the input without changing your answer is what is called mathematical preprocessing or kernelization, which is one of my focus of work. Okay, but it turns out that there is even a simpler observation that yields even a faster algorithm for our problem. And what is that observation? Every conflict has to be resolved, right? Every conflict has to be resolved. What is the meaning of this? So the only way to resolve a conflict is to refuse at least one of the 2 participants of the conflict. So what I mean by this, so imagine that Alice and Bob has a conflict. You definitely know that you cannot admit both. So either you have to refuse Alice or you have to refuse Bob. And that's an idea which we will try to use to design our algorithm. So what our algorithm does is that, okay, I know I have to reject either Alice or Bob. Let's try to do the following. Let's try to reject Alice. Let's not disallow Alice to come, and say in the remaining, can I manage without k minus 1 people? Like, can we just throw at most k minus 1 people and be happy? I have decided to throw Alice. If this succeeds, you already have a solution. Else, if it fails, then you know, after I removed Alice, I couldn't find a solution. Let me try restate Alice. Let's try to remove Bob, and let's try to see if I could find a solution with at most k minus 1 people. I try, right? And do what we did with Alice. So this is what is known as recursively trying to solve a problem. Okay. If this also recursive algorithm fails to find a solution, then what can you say is that there is no way to avoid a fight by rejecting at most k guests. And this is exactly how the looks like. So you have Alice and Bob. I try to see if what happens if I try to reject Alice. Can I get to a solution? Oh, but if I succeed, great, but all of these has failed. So I try to reject Bob. from my list and try to find a solution on the remaining instance in the right side. Okay? So in the leaves marked with fail tells you that, look, I have already deleted some k people, but there's still some unresolved conflicts. Okay? And here it basically on this says that, look, if you delete Bob, Daniel and Feder, then you are able to take care of all the conflict. So this is a good or valid solution for k equal to 3. Okay? Okay, so what's the running time of this algorithm? Okay? All we did, check whether all conflicts have been resolved. That is all that we do. And if not, it makes 2 recursive calls. Both of the recursive calls, the value of k decreases by 1. Okay? So the total number of recursive calls that it will make is 2 power k, because this is a tree whose total number of nodes is 2 power k. You can check. Okay? And running time is roughly 2 power k n plus n. But if you recall, we said that, whatever the pre-processing we were trying to do, we could get down the number of vertices plus number of edges to n plus n was like 3k squared, because we had k square conflicts and there were 2k square people involved in this conflict, so total was 3k square. Now if I put down this number 2k k square, which is roughly 2 power 10 into 10 to the power 4, which takes a fraction of a second on today's laptop. So you could solve a problem if you try both these heuristics. Once you apply this heuristic, you try this way of recursively trying to find a solution, then you are done. Okay? Okay, so that was a little bit of trying to tell you some algorithms. Now, in fact, now you can solve this on cell phone, because someone has coded this algorithm on the cell phone and you could actually run this. Okay, so what is the message? The message is very simple. We were trying to exploit the solution size as a guiding force to design an algorithm, right? So, which basically means that, for any problems, there are much more than the number of people, the sizes, but there are much more that could be exploited. And this thinking that, let's try to use this structure, this something more than the input size, is what has led to this world of multivariate algorithms or parameterized complexity, as Venkatesh put it in his introductory remark. Okay, so here is a distinction between classical versus multivariate. So what is a classical? That you're given input to the problem, a number n, and a question that needs to be resolved. And in the multivariate thing, you're also given an aspect of the input that constitutes what is known as parameter, the number k, and the question that needs to be resolved. Okay, so for example, if I have to model the question which we were trying to do before, so this is what GP5 prevention problem is. There's some graph, integer k, and we are asking, does there exist k size subset of vertices such that when I delete s from G, it has no conflict, it means it has no edge, what is known in classical literature as independent set. So can I delete k vertices so that what I get to is an independent set? Okay, so let's try to understand what is this multivariate algorithm tries to do, what kind of algorithms that it tries to capture. Okay, so while in the what is known as fixed parameter tractable algorithms is that the input is still old classical polynomial, like n to the power c, like n to the power 2, n to the power 3, but I allow your running time dependence on the number k to be exponential. It could be any function of k. We do not stop it from n, and till we have not resolved this p versus np question, this is one way to get a correct set of answer by allowing some aspect of the parameter exponential dependence or any dependence on the function of k. Okay, so this is the area where I have been working on for last 2 decades, is that the kind of algorithms I try to design, we have an input, we have a parameter, and we try to ask ourselves question, could we have such kind of algorithm for this problem? But as has been the classical complexity, not every problem has an efficient solution. In this world also, not every answer is good. There are all kinds of answers. So what kind of question do we ask? The first question we ask, given this, can we design such an algorithm? Once we have designed any f of k algorithm, the second question asks, okay, That's fine that you have shown that such, for example, even in the classical world, you saw n cube algorithm, you try to say whether I can do n square or not. Can I do n log n or not? Or can I show that n log n is not possible under some hypothesis? So similarly here, now you play game with f of k. Can I do f of k? How small can I do? Okay? How small can the dependence on the n be? How small the independence on the input size be? Okay? How small the dependence on both f of k and n together could be. So you can ask all kind of questions. Is there a possible way of ruling out that this kind of algorithm is possible, but this kind of algorithm is not possible? Okay? This exists, but this does not exist. Like, you can ask all kind of questions, and of course we try to show such kind of lower bounds under some complexity theory assumption that, okay, if, as I told you, right, if such kind of vacuum cleaner will exist, then blah blah will happen. So most of the complexity theory, the lower bounds are of this nature, that something bad happens. Like, if you could design something so good, then something bad could happen, which we do not believe that kind of bad should happen. Okay? So these are the kind of questions we ask in this world. So here the message of this multivariate algorithms is the following. So you like to measure the running time of your algorithms, both in terms of your input size as well as parameter that captures structural properties of input instance. Okay? And now the area has permeated to all kinds of domains. There's nothing but graphs. It's like, such as your input could be set system, matrices, matroids, polytope, lattices, some topological space, you name it. As well as you could mix it with any kind of paradigm, such as approximation algorithm, preprocessing, heuristics, machine learning, dynamic algorithms, and streaming algorithms. So basically it is just a way to phrase your question. So once you have a paradigm to phrase your question, you could always mix it with any other paradigm and ask some important and central question. Okay. Okay, so this is what my contribution to multivariate algorithms has been, which I have put it into this art or whatever it is called. And there are a couple of books which we wrote. So if someone has more interest, they could go have a look at these books, and they will know more about the area of parameterized algorithms. And if someone is interested in polynomial-time preprocessing or mathematical preprocessing, then that's a green book. And that's all that I wanted to say. Thanks for your attention.
Thank you, Saket. Are there any questions?
Is there any quantum algorithm for that problem?
Yes, there are.
Okay.
There are quantum algorithms also. People have also studied quantum parameterized algorithms, and people have designed quantum vertex cover algorithm. So just like any classical algorithm, here also the running time actually becomes square root of that.
Okay.
Any other? Yeah.
So in the real world, I think you said something about you might prefer a polynomial time algorithm to exponential depending on what the input size is and prefactor. My question is more like, how much do computer scientists worry about that you've got a polynomial time algorithm, but on real data it will actually be worse, and an exponential algorithm is actually useful?
Yes, so like people do worry about it, and now there is whole lot of new community which is coming up, which is trying to do very fine-grained complexity inside P. So for example, for some of the old very classical problem, you have a very well-known lower bound like n cube. Now if they try to say, look, if my input is coming from much more structured, can we break this n cube, get it to linear or n squared? And now people have tried to prove either good algorithms exploiting the structure of these instances, or even there they say, look, I mean, this structure did not help, because we could still prove a lower bound. So there is a whole community, at least in last 1 decade, which has developed, at least for the very well studied, like shortest path and all paired path. People have tried to do such kind of structural study, and where when they go on this structure, the running time dependence could be exponential. And they seem to say that empirically some of these algorithms run very much better. So your answer to is yes. People at least theoretically have started to worry about these things.
And the follow-up, I mean, you also mentioned heuristics like removing the node, the worst guy, the fighter node, and so on. So in bioinformatics, for example, most algorithms end up being heuristic because the problem is but so it will fail on some input, but on most input it either works or it gives an answer that is good enough. So in a problem like this fight resolution, you might have you want to remove k people, and you find an answer, but it turns out you could also remove k minus 1 and you don't find that answer.
Correct.
So what are the trade-offs in a computer scientist's mind in thinking about these things?
So up to k is perfectly fine, but then also like people look, this is just a paradigm where I have decided that I only allow up to k. But there are also paradigms where I say, look, I'm very happy that I gave you this number k. You could come up with a heuristic where, but I still want some sort of guarantee that you guarantee me that whatever happens, either you tell me that with at most k people, no, I cannot, or you are able to give me a solution with say 2k people or 3k people, right? So people have also started to now come up with these kind of heuristic, which is loosely correct. Let's say loosely correct. So there is also a paradigm. So at least in my book, I write a chapter where actually we can prove that for some of the problems which we study, we cannot have this kind of completely concrete heuristic, but real heuristics or exact heuristic. But if we allow slightly approximation, slightly loss, we are able to do it. So people have started to study it, but not a lot has happened over it. But like for example, Jeff, for this kind of compression, we do have lot of lossy compression. So yes, we are trying to study that, but the theory is still very, I would say, nascent.
Okay, thank you.
Any questions from YouTube?
You were talking about approximate solutions, right? So sometimes maybe we have some partial information about the system that maybe we don't need to explore all the possibilities. So can we use that partial information to narrow down the solutions?
Yes. So like in computer science, we all study all kind of, like sometimes your model is completely as a black box to you. Sometimes you only can get this information using some query or and based on that you try to do. So these kind of questions has also been studied, and at least in many cases it will lead to some interesting answer, but many times we can also prove that until you reveal my whole data, we will not be able to say something meaningful. So yes, there's something what is called query complexity, or like you have a model where you can query the input in certain way, and you try to get your answer based on as few queries as possible. So there are also like some part of the data is given to you, and you based on that you try to assess some answer, and then you ask queries to the hidden place. So yeah, these kind of questions have been studied. But I don't know too much about them, but yes, this has been studied.
What about something like coarse graining? So in
something like
coarse graining, like
coarse graining.
Like for example, in that example you were talking about, what if the security guard had information like these group of people don't fight with this group of people, they fight more with another group of people. So look at
that could also be some sort of probabilistic model that people could think, and yes, there could be one could. I have not tried to do that, but people could ask several questions of this thing. For example, like the algorithm which I told you, by nature bias, like why among these two people I would prefer him versus him, like it's like I'm assuming that everybody is equal, but maybe everybody is not equal. That's what you're trying to say, right? Yes, people could like use some sort of weights on these vertices and use that information to model this kind of situation and try to answer it. Yes, that's doable.
Yeah, so there's a question in YouTube by Pawan Mishra. Is K always related to the structure of the problem? Can K be related to something else?
Problem, I wouldn't say the K is related to the problem. K is rather related to the input which we have. And generally, I mean, if K is not related to what we have, we do not know how to exploit that. So I would say that, I mean, K could be anything, but until it is related to my input, it seems that we will not be able to exploit.
The question is K related to the structure of the problem, or can it be related to something else? Okay, maybe you answered it here.
Yeah, so generally it is, but it's not necessary.
Okay, I don't see any more hands. So if there are no more questions, let's all thank Saket again.